Today we will be looking at some wave examples for AP Physics 1. So this first one says, AM and FM radio waves are transverse waves consisting of electric and magnetic disturbances, and they travel at the speed of light, which is 3 times 10 to the 8th meters per second. A station broadcasts an AM radio wave whose frequency is 1230 times 10 to the 3rd hertz, which is 1230 kilohertz, and an FM radio wave whose frequency is 91.9 times 10 to the 6th hertz. Find the distance between adjacent crests in each wave. It's always helpful to figure out exactly what the problem is asking you to solve for, and it words this a little bit differently. So find the distance between adjacent crests in the wave. So these are transverse waves, so they look sinusoidal. So let's say here is my wave, and it wants us to find the distance between adjacent crests. So if we labeled that on here, it's asking us to find that distance, which in reality is our wavelength lambda. So our goal here is to find lambda for the AM radio waves and the FM radio waves. So there are two parts to this problem. It's going to be repetitive, so I will go through the first parts and then show you the work for the second part, since it will be exactly the same. All right, so we have AM radio waves first. Let's list our givens. We know the speed is just the speed of light, since this is a radio wave and that's an electromagnetic wave. So that's 3 times 10 to the 8th meters per second. We know that the frequency F is 1230 times 10 to the 3rd hertz. And we are trying to solve for lambda, the wavelength. We have a wave equation, which is lambda is equal to speed over frequency. So all we have to do is plug this in. Lambda equals 3 times 10 to the 8th meters per second divided by 1230 times 10 to the 3rd hertz. And we get an answer of 244 meters. So AM radio waves have a pretty long wavelength. That is the distance from one crest to another. Next, we have FM radio waves. And our work will be exactly the same. The only difference is the frequency. So it has the same speed since it's still just an electromagnetic wave, but the frequency is 91.9 times 10 to the 6th hertz. And we are looking for lambda. And we get, before we actually say what the answer is, just conceptually, if we think about the relationship between lambda and frequency, wavelength and frequency, if we look at that wave equation at the top, they have an inverse relationship. If I make frequency bigger, I am making wavelength smaller. So according to our givens, FM radio waves have a much higher frequency than AM. So if it has a higher frequency, I would expect a smaller wavelength. It's like those waves are bunching up and they have a smaller wavelength. And if you calculate this, you do get a significantly smaller wavelength. They're 3.26 meters. Let's do a wave on a string example. So it says here that transverse waves travel on each string of an electric guitar after the string is plucked. So imagine you have a guitar. When you pluck that string, you're actually creating transverse waves on the string itself. Similar to how if I had a rope that was tied to a pole and I was holding one end of the rope, moving it up and down, creating transverse waves, same idea there. So you may not be able to see those transverse waves necessarily, but you are creating them as you play. It says that the length of each string between its two fixed ends is 0.628 meters, and the mass for the highest pitched E string is 0.208 grams, And the mass for the lowest pitched E string is 3.32 grams. Each string is under a tension of 226 newtons, and it wants us to find the speeds of the waves on each of the two strings. So this problem also has two parts like the previous one. It's nice when you're working on a physics problem to identify, especially when you have two objects, to identify what they have in common. So in this case, the length L is 0.628 meters for both strings. They have the same length and they also have the same tension. So the force of tension is 226 newtons for both of them. We're solving for the speed of the waves that are traveling through each of the two strings. So we're going to do the high E string first, and then we'll do the low E string. So our equation from our notes is, for the speed of a wave on a string, is speed is equal to the square root of the force of tension divided by the mass divided by the length. And they told us the mass of the high E string is 0.208 grams, and the mass of the low E string is 3.32 grams. Now we will need to convert that to kilograms, so you can write that in scientific notation if you want. 0.208 times 10 to the negative third kilograms, 3.32 times 10 to the negative third kilograms for the low E string. So it looks like all we have to do at this point, we don't have to do any algebra, we are just plugging in. Now, if you want to simplify that equation a little bit, you could, since they gave us mass and length separately, you could write it as force of tension times length divided by mass, and then plug in. So we have 226 newtons times 0.628 meters divided by 0.208 times 10 to the negative third kilograms. And we get our speed for our low E string is 826 meters per second. Very similar work for our low E string. I'm using the same equation. So if we think conceptually before we solve, the low E string has a bigger mass. And if you look at the relationship between speed and mass in that equation, that is an inverse relationship. So if our mass increases, our speed should decrease. Let's see if that is true. So the square root of 226 newtons, our numerator is exactly the same because they have the same tension and the same length. But now we divide by the mass of the low E string, 3.32 times 10 to the negative third kilograms. And we do get a lower speed, 207 meters per second. So the string with the greater mass has a slower velocity. This is a conceptual example about a transverse wave. It looks like we have a wave on a string. It says the speed of a transverse wave on a string is v sub wave, and the speed at which a particle moves is v sub particle. Which of the following statements is correct? So are those two speeds identical or are they different? So our wave is traveling to the right, but if we look at the actual particle on the string, as that wave moves to the right, this point is oscillating up and down like this. And that's what makes this a transverse wave, that the disturbance is perpendicular to the direction the wave is moving. So this is conceptual. We're not going to plug in numbers, but we can think about our equations. So the speed of the wave, this is a wave on a string. So we have an equation for that. That speed is the square root of the force of tension divided by the mass divided by the length of the string. So that's something to start with. And then we need the speed of the particle. Now this little equation is going to come from our simple harmonic motion unit. So the maximum speed of that particle is going to be equal to the amplitude times the angular frequency of the particle. We could rewrite this as amplitude times 2 pi times the frequency, because we learned last unit that omega is equal to 2 pi f. That's actually on your equation sheet for AP Physics 1. So I have this equation for the speed of the wave, and I have this equation for the speed of the particle. And as we can see, these are two very different equations. The speed of the particle doesn't depend on the mass of the string or the length of the string. It just depends on the amplitude and the frequency. And the speed of the wave depends on the tension, the mass, and the length of the string. So that means our answer is that these speeds are going to be different. Our last example has to do with constructive and destructive interference. So we have these two loudspeakers, A and B. They are separated by a distance of 3.2 meters. And then you have a person standing 2.4 meters away from loudspeaker B. And the question is, does the listener hear a loud sound or no sound? Because you have sound waves coming from speaker B traveling 2.4 meters to the person. You have sound waves coming from speaker A traveling some distance to the person. And if there's constructive interference, then those amplitudes should add together, resulting in a louder sound. If there's destructive interference where those waves meet at point C, then the amplitudes are going to cancel out and the person shouldn't hear anything. They also tell us that the triangle ABC is a right triangle. That'll come in handy later. And that both speakers are playing identical 214 hertz tones. Also, the speed of sound is 343 meters per second. So let's go ahead and list that. So we know that the frequency for both, the sound coming from both speakers is 214 hertz. And the speed of sound is 343 meters per second. Now, the fact that they told us this was a right triangle is helpful because we need to think about how far the sound waves are traveling from A, speaker A, to the person at point C. So we do need to find that distance there. We can do that using Pythagorean theorem. So that means that that distance there will be equal to the square root of 3.2 meters squared plus 2.4 meters squared. That gives us a distance of 4 meters from speaker A to the person at point C. So where do we go from here? Conceptually, if we are trying to figure out what will that person hear at position C, we're essentially asking, will the waves line up or will they be out of phase, canceling each other out? So when waves from A reach point C and when waves from B reach point C, we're asking ourselves, are the waves in phase? Will it be constructive interference or will they be slightly off, out of phase from destructive interference? And in order to figure that out, what you end up doing is subtracting the distance that each wave travels. So we'll take the distance from A to C and subtract the distance from B to C. So I'll have 4 meters. That's how far the waves have to travel from A to C, minus 2.4 meters. That's how far they have to travel from B to C. And we end up getting 1.6 meters. That's the difference in the distance the waves are traveling. Now, why is that relevant? Because if we can figure out the wavelength of the sound, and we know that that is the difference in distances the waves are traveling, we can compare that 1.6 meters to the wavelength to figure out if the waves are going to be in phase or out of phase. So how do we figure out the wavelength lambda? We use our wave equation. They gave us V and they gave us F. So that's 343 meters per second divided by 214 hertz. And we get 1.6 meters. So if the wavelength the wavelength of the waves coming from speakers A and B is 1.6 meters, that means that's the distance from one crest to the next crest, or one area of compression to the next, since these are sound waves. So the difference between their path lengths is also 1.6 meters. So that means that the person hears a loud sound because we have constructive interference because our amplitudes are actually going to line up. So yes, we have waves leaving speaker B, and they only have to travel 2.4 meters. I'm kind of just drawing longitudinal waves the best I can. They only have to travel 2.4 meters to get to the person, and then we have waves leaving speaker A, and they have to travel a little bit farther. However, they only have to travel 1.6 meters farther, which is the same distance as the wavelength. So by the time those waves are reaching the speaker, they will constructively interfere there. The long lines I'm representing areas of compression, for example. So you can see that even though the waves from A to C have to travel 1.6 meters farther, since that's equivalent to one wavelength for these waves, you end up having constructive interference there and the person hears a louder sound. I do want to note that this problem is assuming that speakers A and B are oscillating or vibrating in phase with each other. You could have speakers that are out of phase with each other. That is obviously a little bit different, but we are assuming that the speakers are in sync with each other in the first place in order for this to work.